Friends, welcome to BYJU'S Exam Prep. Under this Formula 1 series, today we are going to learn Discrete Mathematics Formula Set 2. We already completed few important topics like Counting Part 1, Sets and Logic Part 1, and in today's session, I am going to continue with the remaining part. That is Logic Part 2, Relations, Functions, Graph Theory and Counting Part 2 formulae. Okay. So, are you ready for this session, my dear friends? Please let me know. Hope, am I audible, visible to all of you? So, today's session, Discrete Mathematics Formula Series Part 2. And this is my Telegram channel. Those who want the PDF of today's session can get that PDF if you join my Telegram group. And the PDF will be password protected. The password, hi sir, the password will be mentioned in today's session. So those who attend can get that password, my dear friends. Okay, and this is about me, myself, Sridhar Dhulipala. I am having 20 plus years of teaching experience and I am associated with, hi sir, good evening. Sanjay Singh, very good evening sir. I am associated with BYJU'S Exam Prep from past 1.5 years. We are working on this particular project called Recorded Gate Content, the first of its kind, and I recorded all these subjects: Discrete Mathematics, Engineering Mathematics, Algorithms, C Programming and Data Structures. If you download the BYJU'S Exam Prep app, under the category Learn with Video Lessons, you can find all the videos which were recorded by me. Those who purchase can get all the videos, my dear friend. Even otherwise, you can go through some of these videos, my dear friends. Okay? So, without wasting much of your time, let me start with Formula Part 2. Of course, discrete mathematics is all about formulae, but that is only 1%. The 99% in mathematics always is how to apply the formulae. Am I clear? So, but if you want to apply, first you should know the formulae. So, I am going to give you the formulae, my dear friends. Are you ready? Ready for the show? Let us start with it. What is a predicate? Predicate or open proposition. It is a proposition. It is a proposition except for the fact that it contains variables. It contains variables whose values are to be taken from some set, and that set is given a beautiful name called universe of discourse, whose values are to be taken from some universe of discourse. So this is the definition of a proposition, predicate or open proposition. It is a proposition except for the fact that it contains variables whose values are to be taken from some set that is called universe of discourse. For example, if you are having x plus 2 is equal to 5. So this is something like p of x, you can call it predicate. The truth or falsity of this particular sentence depend on the value of x. It is ready to be proposition but not proposition. Such open propositions are called predicates, my dear friends, or open propositionally such propositions, that is ready to be propositions but not propositions. Okay, that is what we call it as open proposition or predicate. See, the entire story of this predicate calculus is how to convert these predicates to propositions. And for that we are going to use two quantifiers. One is called universal quantifier, the other one is called existential quantifier. And whenever you talk about this predicate calculus, we need to understand the following: the meaning and the truth value. See, most of the people who learn this predicate calculus always mess up with these two things. We can mean anything, and people always worried about truth value. See, my dear friends, here we are going to symbolize what you mean, not symbolize the truth value. That you need to understand when you want to understand this predicate logic, my dear friends. If you want to understand predicate logic, you should understand the meaning of the form. Of course, truth value comes only when you have a particular universe of discourse, my dear friends. Otherwise, you cannot have the truth value. Am I clear? So, these are the standard forms and their meanings. These are the standard forms and their meanings. If you want to understand predicate logic, you need to understand this, my dear friends. Here, this is a quantifier and this is a predicate. See, for all values of x, px is true. See, that is what I want to say. For all values of x, px is true is what I want to say. For example, if I have this x plus 2 is equal to 5, I can say this is a predicate. I say that p for all x, px, I can say that. Now, suppose my universe is say 1, 2, 3. For all values of x, px is true or false. Whether it is true, hello Kaustubh, whether it is true or false. For all values of x, px is true is a true statement or false statement. Is a true one or false sentence. What do you say about it? Whether it is true or false. Whether it is true or false. This sentence is true or false. For all x, px is true or false. False. See, this is the truth value. But here we are not talking about truth value, sir. We are just talking about meaning. So, truth value comes when you have a universe of discourse. For example, your universe of discourse is say only 3. Your universe of discourse is only 3. For all x, px is what? For all x, px is what? Suppose your universe is only 3, not this. In this particular case, what is this for all x, px? It becomes true or false. My dear friends, please be interactive. If you are not interactive, I'll be reading out all the stories and going. It is of no use for you. It will be true. So this true value depends on the universe of discourse as well as the predicate, my dear friends. But the meaning does not depend on the truth value. Whenever I say for all x, px, what I mean for all values of x, predicate is true. In both the cases, I mean the same. My meaning never changed. That is the for all x, px meaning never changed. What changes is truth value. Truth value is problem instance dependent. Those who cannot understand the difference between the meaning and truth value can never learn this logic in their lifetime, my dear friends. You should always understand the distinction between these two things. That is truth value and the meaning. Here we are symbolizing or we are talking about the meaning of the form, not truth value. Truth value comes at later stage. Because meaning is always same. Na? For all x, px is always same. Meaning is same. So we are talking about meaning of a form, not truth value of a form. Am I clear? Not truth value, meaning. And here you see, for all x, px means for all values of x, simply all, px is true. Simply the predicate is true. You can simply call it as true. So this all represent all values of x. True represent the predicate whatever is given, that is true. That is the meaning of that particular form for all x, px. Now what is the meaning of there is x, px? For some values of x, the predicate is true. So we say some true. Actually, when you say some, you have to be very careful. Some means what? Is it 1, 2 or 3? So we cannot guarantee 3. We cannot guarantee 2. What you can guarantee is 1. So we say at least 1 true. So that is the correct meaning of this. For there exists x, px, my dear friend. There exists x, px meaning is what? At least 1 is true. At least 1 is true. Now what is the meaning of this particular form? See, to understand the meaning of the form, just remember one point, sir. Whether you are negating quantifier or predicate. Whether you are negating quantifier or predicate. If you understand, the rest of the forms are very simple, sir. Here we are negating quantifier. So quantifier says all. What is negation of that? Not all. That's it. Not all true. What it says? Not all true. Next one. Quantifier says at least 1. What is negation of at least 1? What is negation of at least one? No one or none. So this is the best way to say none. See, one important point to be noted here is, which majority of the people never understand, is here we are restricted with just two quantifiers. One is for all, one is there exist. Whatever you want to say, you have to make use of these two fellows and say. You can't say directly anything because you are restriction. You are having a restriction. Anything you have to say using universal quantifier or existential quantifier. So the best way to say none is write at least, because you are having that particular format, negate it. What is negation of at least one? None. That is the idea. Got it? Then what is it? Here what is happening? Are you negating quantifier or a predicate? Are you negating quantifier or predicate in this case? Here we are negating the predicate. So all, whatever predicate is given, that is false. Predicate Px means predicate is true. Negation Px means predicate is false. That is all false. That's what it is. And here some false or at least one false. And here both quantifier as well as predicate negated. Not all false. Not all, not true. Not true means false. Good evening, sir. Very, very good evening. Next comes negation there exist. That is none, not true. That is none false. That's it. After knowing the 8 forms and their meanings, what we need to understand is the relation between them. When you say all true, what does it mean, sir? All true means nothing is wrong. Everyone is good. So no one is bad. If you say some true means at least one true means not everyone is bad. Not all bad. Am I clear? At least one good means not everyone is bad. Correct or not? So they have equivalence. They are equivalent. Similarly, not all true means koi hai, there is someone, there is some idiot. That is it. Not all true means at least someone is there bad fellow. And none true means everything is false. None true is everything is false. So by understanding the meaning, we can also find the relation between these meanings, and we found 4 new equivalences. Earlier we done some equivalences, 3 parts. One is equivalences involving conjunction, disjunction and negation. Second is equivalence involving implication. Third one is equivalence involving by implication. Now we got the 4th type of equivalence, which is equivalences, which you just now identified. That is, for all x px is equivalent to negation there exists x negation px. There exists x px equal to negation for all x negation px. Negation for all x px is there exists x negation px. And finally, negation there exists x px is for all x negation px. So those 4 equivalences we get it, my dear friends, from what we observed. So these are the 4 important equivalences. And these equivalences will give you the idea of how to negate the quantified predicates. This will give you the idea of negating quantified predicates. Negating quantified predicates. If you see this rule, negation for all x px is equivalent to what, sir? There exists x negation px. If you observe this, you want to take negation inside for all changes to there exist, and the predicate is negated. Similarly, if you want to take negation inside there exists x converted to for all x, and the predicate is negated. That's it. Okay. So this is one of the important topic, and many GATE questions were asked on this negating quantified predicate, my dear friends. One of the important concept. The rules of inference for quantified predicates. We already know 12 rules of inference for propositions. See, ultimately predicates also need to be converted towards a proposition. They are propositions only. Only they have some problems. So that problem can be rectified either by making substitutions or by quantifying. So once you quantify, they are propositions only. Am I clear? So how to convert the predicate into proposition is one of the important tasks, my dear friends, and that is what we are going to do here. Am I clear? See, first one is specification. Suppose you are having something, say, for all x px. Then instead of that x, you can put any value of a, my dear friends. You can put any value of a. Suppose for all x px is true, then you can put x any value, pa for any way. This is called specification. This is what we call it as universal specification. Similarly, existential specification. If you say there exists xpx means, here we can't say PA for any A, because at least for one value it is true. Guaranteed is 1. So we take PA for some A. Even though we say for some A, we can only guaranteedly take one A only, sir. That has to be fixed. Now what generally we do is, once you have a some argument in predicate form or argument in the form of this quantified predicate form, that you convert into propositional form. Using specifications. You convert into propositional form. This is predicate form. Of course, quantified predicate form. You have a quantified predicate form where you have an argument. Using specification, you can convert into propositional form. Once it is propositional form, you have rules. Using that rules, you can verify some, or you can make some conclusions. So make some conclusions using our rules of inference. Make the conclusion. But that conclusion is in propositional format. What you do is, you use generalizations. To get conclusion in predicate format. Here conclusion is in propositional format. You get the conclusion in predicate format, my dear friends. And for that we need this generalization rules. Suppose PA is true for any A, you can make it true for all X. Suppose PA is true only for few values of A, then you can say there exists XPX, my dear friends. So this is the idea for this generalizations as well as specifications. One of the important topic, and directly these results only asked in GATE examination, sir. Directly these results were asked in GATE examination. Here I am going to give 3 parts. These are direct GATE questions. Direct results were asked in GATE question. I'll give you a simple method to remember them. For all works fine with AND connective. There exist works fine with OR connective. Correct? For all works fine with AND connective. Therefore, for all x, px and qx is equivalent to for all x px and for all x qx. Similarly, there exist with OR is equivalence. But for all with OR, there exist with AND works only in one direction. For all with OR and there exist with AND works in only one direction. That is, for all x px or for all x qx implies for all x px or qx, but not reverse order. This reverse order, it won't work. Whereas similarly, there exist x px and qx is implying, logically implying, there exist x px and there exist x qx, but not reverse order. And we also have this result. This is the most important result, sir. You can see 4 GATE questions directly based on this. If you know this, directly 4 answers would be correct, and you will get 4 times 2 marks, my dear friends, in GATE examination. That is the most important result. For all x px implies qx is equivalent to, not equivalent to one side condition. For all x p implies, that is px implies q, is logically implying for all x px implies for all x qx, but not reverse order, my dear friends. Actually, this is very important. These 3, if you can practice well, because these 2 you can easily remember, because for all works fine with AND, there exist works fine with OR because of their definitions. These 3 you have to practice, sir. Out of 12, these are the 3 which you need to practice. But suppose if you are having one predicate and one propositions, all the first four will be equivalences only. Sir, for the first and second there is a triple equal sign. Yeah, that's what I said, sir. This is equivalence. Two-sided condition. Two-sided condition means left side दिया तो right side लिख सकते हो, right side दिया तो left side लिख सकते हो. If you given left side, you given right side. If it is right side is given, you can get right left side. Two-sided condition. Whereas this is logical implication. See, logical implication is one-sided. One-sided means left side is given, that can be replaced with right side, not vice versa. Vice versa नहीं कर सकते हो. You cannot do it in the reverse order, my dear friends. Now here, when you have one predicate and one proposition, first 4 will be equivalent only. These 4 will be equivalent only, my dear friends. Easy situation. One predicate, one proposition. For all works fine with AND OR. There exist also works fine with AND OR. And these are the important ones which we need to remember. For all with One predicate and one proposition. One predicate and one proposition. If the first one is proposition, there exist or for all can be distributed directly. For all will be distributed to predicate. There exist will be distributed to predicate. Okay, in the same order. But if you are having first predicate, second proposition, I'll just prove one of them, sir. Third one, if you see, it's a very simple problem actually. For all x, px implies q. By law of implication, this can be written as negation px or q. And as I told you, when you have one predicate and one proposition, for all can be happily distributed to the predicate part. That is for all x, negation px or q. And you can take negation outside so that it becomes negation there exists x px or q. And here you can apply law of implication, therefore it becomes there exists x px implies q. So these are all simple problems, my dear friends. You can easily solve it. So these are the 4 important results, my dear friend. Total I given 3 parts, quantifier and connectives. These 3 parts were asked in GATE very regularly, standard result. Many times they ask these results directly in the examination, sir. Practice them. Okay? I also told you how to remember them. Then comes statements into symbolic form. For statement into symbolic form, we are going to use the ideas given by father of logic, that is Aristotle. Okay? And even today, they are the best equivalent forms for the given statement. See, here there is no proof, my dear friend. Here this is not about proof. What is the best symbolic representation for a given statement? That is how we need to understand. And here also people have some misunderstanding, like, for all should be followed by implication. It's not like for all should be followed by implication. We can also have statement where for all can be followed by disjunction or conjunction also. The idea is for all, when it is used in a particular sense, will be followed by implication. And what is that sense, sir? That is given by none other than Aristotle. That's why we call them as Aristotelian forms or Aristotle forms, my dear friends. And the first one is all P's are Q's. See, whenever your statement is given in this sense, that is important. Whenever your statement is given in this particular sense, like all birds can fly, all my students are intelligent, all student goes to movies, all student jump. Whenever you are having the statement in that particular sense, for all will be followed by implication. Don't blindly say that for all followed by implication, you will go to jail. Be careful. So for this, the form is for all x, px implies qx. So you can easily write this, sir, like, all birds can fly. So what is it? For all x, bx imply fx. That's it, over. Good evening, sir, and all my friends. Nishu Kumar, welcome, sir. Similarly, some p's are q's. See, here also when some is used in this particular sense, there exist will be followed by conjunction. It's not like there exist means conjunction. There exist used in this sense, then there exist followed by conjunction. Some students join late. Some students are late to the class. Nishu Kumar. Okay. Some students are intelligent. Some birds can fly. Now all these things. Okay. So in GATE there was a question. Some real number or rational number, whatever, I don't know exactly, but whatever it is. Don't worry about truth value, sir. Some rationals are real. This was a direct GATE question, 2 marks GATE question, sir. So simply write there exists x, rational x and real x. Directly you will get it, my dear friends. So there exists x, px and qx. See, what is very important is when some is used in this sense, some p's are q's sense, some followed by conjunction. Then comes not all p's are q's. Here what is negated? What is negated? Predicate ya quantifier. What is negated here? What is negated here? What is negated here? Quantifier is negated, not all. You said not all. क्या बोले थे हमने? Not all बोले थे. यानी all को आपने negate किए थे. Quantifier को negate किए थे. We not negated the predicate. Okay? So पहले all P's are Q's लिख दो. All P's are Q's and say sorry to it. अभी negation किसको हुआ है? You are negating what? For all. That is it. And if you use negating quantified predicate, this can also be written as there exists X. Okay, negation will go inside. So what is negation? P implies Q, my dear friends, which is P and negation Q. So this would be Px and negation Qx. Means what? Some P's are not Q's. See, when you say not all P's are Q's, what is the meaning of that? Some P's are not Q's. I could able to get that particular meaning by the symbolic form. Not by analyzing this, I got this meaning, sir. By symbolic form, I could able to get the equivalent statement. That is the beauty of this, my dear friends. Can you explain in English which one, sir? Vishnu Perumai. I think I am doing it in English only, right? Let me remove this. See here, not all P's are Q's. So here, are we negating quantifier or we are negating predicate? We are negating quantifier. So here what is negated? Not all. Quantifier is negated. So first keep it on a hold. Write this. For all x, px implies qx. Happily write down. Then what you need to do? Say sorry. Not means sorry. Sorry, Babu. Is that clear? You are negating quantifier, not predicate. Now you can take negation inside. I already given how to negate the quantified predicate. Then negation goes inside. For all will change to there exist. It becomes negation px implies qx. And I told you already negation of p implies q is equivalent to what? P and negation q. So with that, you are going to get there exists x, px and negation qx. Mr. Perumai, is that clear? What it says? Some p's are not q's. See, when you actually say not all p's are q's, what is the matlab? What is the meaning? When you say not all p's are q's, what is the meaning? The meaning is some p's are not q's. And I could able to get that English translation by symbolic forms. That is a beauty, and these forms were given by none other than Mr. Aristotle, the father of logic. Now, no p's are q's. See how to say no or none. The best way to say none is say some and say sorry. So write down some p's are q's and say sorry. That's it. So when you take negation inside, it becomes for all x. Negation of p and q can be written as, negation of p and q can be written as p implies negation qx. See, for first year student, there was a C language which was conducted by me, complete C language. It is available. Please go through it. We are planning to come up with some more classes, not just for first year student, for all the students, my dear friends, in the near future. Stay tuned, stay connected. Am I clear? We are coming up with more. And this is the relation between quantified two-place predicate. It is the relation between quantified two-place predicates, my dear friends. See, in this, at the top level, for all x, for all y can imply for all y, for all x, and again for all y, for all x can imply for all x, for all y. That is, they are equivalent. See, two-sided arrow means equivalence. At the bottom level also they are equivalent, sir. Stay tuned, guys. Yes, stay tuned. Now comes this one. This is the one which you remember. Oh, there is something missing now. Don't worry, I'll write it. For all x there is a y. What is missing? Let me write. Just write it in the reverse order, sir. For all x, there is a y. Actually, there is a y. For all x can imply for all x, there is a y, not reverse order. If you just remember this, the rest of the thing is very simple. At the top level, for all x, for all y can imply for all y, for all x. At the bottom level, there exists x, there exists y, there exists y, there exists x, they are equivalent. Only this is what you need to remember. For this, I just give you some simple examples, sir. Single y which works for all x. Single y which works for all x such that x plus y is equal to x. Can you tell me what is that single x, Babu? Can you tell me what is that single x? What is that single y, my dear friends? Y1, sir. Akhil, I don't want x, I want y only. Y0 works for every x. So that is single y is 0. And it is true or not? Is it true or not? I am talking about truth value this time. Is it true or false? Single y works for all x, where x and y are integers. Is it true or not? My dear friends, I am shouting so that you can shout. Answer. Yes, it is true. Now, whenever it is true, can I interchange for all x there is a y such that x plus y is equal to x? So, for every x I can find a y and that y is same y. So, it is also true. Whenever this is true, this is also true. Whenever that is true, this is also true, but not vice versa. Not vice versa. For example, you see, for all x there is a y, x plus y is equal to 0. For every x you can find a y. For every x you can find a y. And that y is, what is that y here? Can you tell me what is that y here? Is it true? If it is true, what is that y? If it is true, what is that y? Minus x. So that y is minus x. So here it is true. But can you do it in reverse order? Can you do it in the reverse order? That is, there is a y for all x, x plus y is 0. That is single y working for every x. Can you fix the y here? Can you fix the y here? Can you fix the y here? That is, for example, y is minus 2. Can you fix y is minus 2? Can you fix y minus 2? Kar sakte ho? Can you do that? No. That means it is false. So whenever this is true, you can't say this is true. But whenever this is true, this will happen. So there is a y for all x can imply this. But for all x, there is a y cannot imply reverse order. So this, if you remember, here just in place of y, you put x. In place of x, you put y. You get these two parts. And this is the complete relation table. And in GATE examination, many questions were asked based on this particular relation. See, you have to identify, like, they give you something like for all x, for all y, pxy can imply for all y, there is a x, pxy. They'll ask you whether it is true or false. Just see from here to here, can you reach? Yes, we have direction, you can reach. So it is true. But if they ask you something like, there is a x for all y, pxy can imply for all x, there is a y, pxy. Can you reach? Can you do this? Can you do this, sir? Please tell me. Can you do this? That is, from here to here, can you reach? Not here. From here to here. From here to here, can you reach? No, so it is false. So this type of question they'll ask you, if you know this particular diagram, such type of questions can be answered within no time, my dear friends. So this is one of the most important relation, my dear friends, relation between quantified to to place predicate. Please do remember this. It will be very, very handy, very, very useful, very, very powerful also. So something is missing. We written that. Now look here. We move on to the relations topic. Actually, relations, we do it in two parts. One is relations, where we just understand what is a relation. Then we try to see relations on A. So first we do relations function, then relations on A, like what are the reflexive, irreflexive, symmetric, asymmetric, antisymmetric, transitive relations and their properties. Okay. Are you ready? Are you ready? Right. So these are some general properties, sir. Cross product. Suppose A is having M elements and B is having N elements, then A cross B contain how many elements? Set of all ordered pairs, it will contain how many elements, sir? M into N elements. M into N elements. So here we'll be going with really fast, sir, because these are many. Not yet revealed the password. It will be revealed soon. It will be revealed soon. Okay? Stay tuned. See, actually I thought of giving a problem whose solution is password. But little over it would be, so I thought, let me give you the password. Properties of cross product. See, what is number of elements in power set of A cross B? Number of elements in power set of A cross B. Power set means what? Set of all subsets. How many subsets are there for A cross B? If A cross B contain Mn elements, the power set or number of subsets is given by, what is the answer? What is the answer? What is the answer? 2 power Mn. Next one. If A contain M elements, B contain elements, then number of subsets of A cross B. Whether you ask number of subsets of A cross B or whether you ask number of elements in power set of A cross B, they are one and the same, and that is 2 power Mn, my dear friends. That is 2 power Mn. Very good. Kaushalya, very, very good, beautiful, wonderful, powerful, nice. A contains M elements, B contains N elements. Number of elements in A cross A. How many elements are there in A cross A? Same number of subsets of A cross A. See, first of all, A cross A contain how many elements? Okay, that is what he asked, na? How many elements it contains? M is there, no? Let me use M only. M square. Very good, Nishu, very good. And number of elements in power set of A cross A would be 2 power M square. Super. Straightforward result. See, one thing, if you understand what definitions I am giving, you need not waste your energy and time, sir. See, first thing which we need to understand is a relation is a set. Relation is a set of ordered pair. Means it is a set. So once it is a set, you can do all the operations which you can perform on a set. For example, suppose R and S are any two relations, you can do union. You can do intersection because they are sets. On sets we can do union. Union means what, sir? Elements from this, elements from set A or set B or both. Similarly, union of relations means elements from relation R or elements from relation S or both. That's what. Either A or B. Here R is used in inclusive sense. R is used in inclusive sense. Similarly, intersection means belong to both and belonging to relation R, relation S. Similarly, difference. Same as sets, my dear friends. If you just understand that relations are sets, all these are straightforward, my dear friends. Whatever it is, sir, it is a set. See, I am not worried about, whether it is subset of some nonsense or what. I am just understanding it is a set. I can do all set operations on this. I can do all set operations on this. That is what I am saying. I can do difference. I can do complement. I can do symmetric difference also. All this can be done. But one special thing which we can do is, inverse of a relation. This is not possible for sets, sir. Inverse of a relation. See, if R is a relation from A to B, then we have a relation from B to A that is called R inverse. It is just set of all reverse ordered pairs. It is set of all ordered pairs BA such that AB is in R. So for every relation, we can have an inverse relation. Remember, sir, for every function, we may not have inverse, but for every relation, we have inverse relation. Don't get confused. And if R and S are two relations, we have three beautiful relations. They can be asked in GATE, my dear friends. See, in GATE, now when they introduce this MSQs, this type of questions are very important. Which of the following is true? Which of the following is false? In such cases, you get these relations, my dear friends. Don't have to study all the properties in the world, sir. Standard ones which are very important. If you know it, that is good for health. If R is subset of S, relation R is subset of relation S, R inverse is also subset of S inverse. Not only that, the inverse of intersection is intersection of inverses. Inverse of intersection is intersection of inverses. Similarly, inverse of union is union of inverses. Am I clear? And this one we already said. What is a relation, my dear friends? A relation from set A to B is actually, so we need to understand relation from set A to set B. What is the definition, sir? A relation from set A to B is actually a subset of A cross B. So if we ask how many relations are there from set A to set B, it is same as asking how many subsets are there for A cross B. Asking number of relations from set A to set B is exactly same as asking number of subsets of A cross B. Because a relation means what, sir? A relation is a subset of A cross B. Means every relation is obviously a subset of A cross B. If you want to know number of relations from set A to set B, you are just finding number of subsets of A cross B and you already know it. If A is containing M elements, B is containing N elements, number of subsets of A cross B is 2 power Mn. Number of relations from A cross B is 2 power Mn. Composition is one more interesting concept. If R is a binary relation from A to B, S is a binary relation from B to C, that is A to B, R is a relation, B to C, S is a relation. The composite relation is directly from A to C, my dear friends. And how it is defined? It is set of all ordered pairs AC such that there exists a B element in set B such that AB, see AB is in AB related with respect to R and BC related with respect to S, then AC will be related with respect to RS. That is how the composition will be formed, my dear friends. Yes, F circle G, see that is about functions, sir. Nishu Kumar, don't get confused with functions and relations. Here we are talking about relations, my dear friends. That is about functions. We'll come to that in a while. Just have a patience. Himmat se kaam lo. Now, if a relation R is defined from set A to A, it is subset of A cross A. It is subset of A cross A. So we can have this, if it is from A to B, we can have RS. But if it is A to A, you can also have this R square. R square is what, sir? RR. R cube is what, sir? R square composition with R. And R power n is what, sir? R power n minus 1 R. It's a recursive formulation. My dear friends. Now let us see functions and their properties. A function from set A to set B. A function from set A to set B is a rule which assigns every element of set A to a unique element of set B. Every element of set A is assigned to a unique element of set B, and we give a name for that fx. It is called image, and we generally denote it by some y, my dear friends. Some y. So we write f is a mapping from A to B, my dear friends. Now let us see the terminology one should understand. Yeah, when f is a mapping from A to B, f is a function from A to B. A is called domain. A is called what, sir? Domain of the function. Now B is not called range. Most of the people confuse with this. B is just a codomain. B is a codomain. And y is equal to fx. See, for example, if it is x, then it is f of x. Now this is y is equal to fx. This is called image. Image of x under f. It is image of x under the mapping or function f. And x is pre-image of y under f. X is pre-image of y under f. See, for this fx, x becomes pre-image. X becomes pre-image. See, if you see in the mirror, what you see inside the mirror is image, and for that image, you are pre-image. Yes. So for x, fx is the image, and for fx, x becomes pre-image. That's it. Note this point, Babu. Images must be in codomain, pre-images must be in domain. It looks silly, but these are very important points to be noted. Okay, please note that. And let us see some results. If f is a mapping from A to B, see, when you are having a function, it may so happen that the mapping only to a part, my dear friends. We may not map to every element. Suppose it is 1, 2, 3, it is A, B, C, D. That is, the elements are only mapped to some elements of B. In this particular case, what happened? FA is a strict subset of B. In that case, we call it as into function. Such a function is called into function. And FA may be equal to B. For example, you see here 1, 2, 3, A, B. Here 1 map to A, 2 map to A, 3 map to B. Here every element of B is having a pre-image. This function is called onto function. Here the image set is codomain. If codomain is range, actually that image set is what we call it as range, sir. So if range is equal to codomain, we call it as onto function. It is called onto function. If range is strictly subset or proper subset of codomain, we call into function. But whatever may be the case, in general, the range is subset of codomain. Onto function means what, sir? For every element in Y or every element in set B, you can find a pre-image. So, for every element Y in B, I can find a X in A such that fx is equal to y. That is, x is pre-image of that y, my dear friends. That is what you mean by onto function. That is what you mean by onto function. Next comes one-one function or injective function. What do you mean by injective function, my dear friends? See, injective function says, okay, diagram is missing, so let me give you. See, injective function says is, if x1 and x2 are different, their images must be different. If x1 and x2 are different, their images must be different. If they are different, their images must be different. Actually, in logic, we study this law of contrapositive. P implies Q is equivalent to negation Q implies negation P. So, what is the contrapositive for this? Because this is equivalent to the contrapositive. Contrapositive means negation of this implies this. That is fx1 equal to fx2, then x1 equal to x2. So this is what we actually use to verify 1, 1 or not, my dear friends. Because it is easy to verify, whereas this is very, very difficult. Because you have to take every two combination and check whether they are not equal or not. Then we have to check their images are not equal or not. So that is very complicated. Therefore, this is the easiest method to verify 1, 1 function, my dear friend, which is actually contrapositive of the given statement. So what we need to understand is 1, 1 means different elements should have different images. Different elements should have different images, my dear friends. And f inverse is possible only when the function is both 1, 1 and onto. That is what you mean by bijection. Bijection means what, sir? Both 1, 1 and onto. Then only we can have inverse, my dear friends. See, for example, you consider this function. You consider this particular function. Okay? This is Neither 1, 1 nor onto. If you do the reverse part, it cannot be a function. Now look at this, sir. This is onto function, but not 1, 1. So if you try the reverse, that is B to A, if you consider, that is not a function, because one element is having two images, therefore it cannot be a function. Now look at this. This is 1, 1, not onto, but when you do reverse, it cannot be a function, because C is not having any image. So inverse cannot be a function. Only when the function is 1, 1 and onto, inverse also becomes function. Otherwise inverse cannot be a function. Only function is invertible, that is f inverse exists when it is both 1, 1 and onto, my dear friends. Only when it is 1, 1 and onto. Now this is a very interesting result which was asked in GATE also. Suppose C1 and C2 are subsets of A. C1 and C2, A is domain, B is codomain. C1, C2 are subsets of A. F of C1 union C2 is equal to f of C1 union f of C2. But f of C1 intersection C2 is not equivalent to f of C1 intersection f of C2. It is only a subset, my dear friends. But here also, if you want equality, the function must be 1, 1. When the function is 1, 1, even this result happens for intersection. Otherwise, it is only for union, my dear friends. Am I clear? Yes. Not range is equal to codomain, sir. Even if range is codomain also, range is codomain, that is only onto function, sir. That is onto function. Range codomain होने से कुछ नहीं होता है. 1, 1 होने से होता है. 1, 1 should be happening. Nishu, 1, 1 should be happening. Now, see, most of the people worry about this inverse. Actually, inverse is very friendly, sir. Normal functions are dangerous because they may not be 1, 1, they may not be onto. So there may be many possibilities. But when it is invertible, it is both 1, 1 and onto. It is both 1, 1 and onto. And in that particular case, because 1, 1 and onto means this result works for 1, 1 function. This always works. So it only works. That is f of C1 intersection C2 is equal to f of C1 intersection f of C2 works only for 1, 1 function. But when you say f is invertible, it is obviously 1, 1. So here, both the results hold good, my dear friends. See, don't see it as f inverse. Just see it as a function, which is 1, 1 and onto. Just see it as a function which is 1, 1 and onto. Therefore, both results hold good. It is a direct gate question, my dear friends. Hello, Tushar. Very good evening, sir. Then counting functions. Counting functions. Am I clear? Suppose A contains n elements and B contains m elements. Then number of functions from A to B is given by number of elements in B power number of elements in A. Suppose you are having a mapping from set A to set B. A is having 3 elements and B is having 4 elements. Then number of functions is given by number of elements in B power number of elements in A. That is 4 cube, my dear friends. Thank you, Anu, Ajay, very thank you for your comment. Is the idea clear? So that is about number of functions, my dear friends. Then comes number of 1, 1 functions. See, for 1, 1 functions, it is number of elements in B, P, permutations, A. Number of elements in B, P, A, my dear friends. So and here, for 1, 1 functions, look at this, my dear friends. For 1, 1 function, can you have a 1, 1 function here? Can you have a 1, 1 function here? Can you have a 1, 1 function here? Let me do this. Can you have a 1, 1 function here? No. So number of elements in A should be either less than or equal to B. That condition must be holding. Okay, so that condition you should always know, my dear friends. Am I clear? So here, A contains n elements and B contains m elements. Here, n should be less than or equal to m, please remember. So this should be smaller than m. And suppose A contains 4 elements, B contains 6 elements. Number of 1-1 functions, how many? How many 1-1 functions are there? Direct formulas, sir. These are direct formulas. What is, how many 1-1 functions are there? How many 1-1 functions are there? So number of 1-1 functions are given by 6p4, my dear friends. Number of elements in B, P, number of elements in A. 6p4 you have to do it. That is 6 factorial by 6 minus 4. That is 2 factorial. So that is the answer, my dear friends. That is the answer. Very good, Nishu. Very, very well done. Suppose A contain 4 elements, B contain 4 elements, number of 1-1 functions. How many 1-1 functions are there? Yeah, very good. 6 into 5 into 4 into 3. Wonderful. Correct. $360. How many 1-1 functions are there? 4 factorial. That is 24. Suppose there is a set A containing 4 elements, set B containing 4 elements, and one function is selected randomly from set function is selected randomly from set A to set B. What is the probability that it is a 1-1 function? That is a randomly selected function from set A to set B. What is the probability that it is 1-1 function? DCS means what, sir? Discrete structures, or what you mean by that? DCS. Discrete structures you mean? Or data structures? I don't know what is that, because some people call it as discrete mathematics, some people call it as discrete structures, some people call it as MFCS, Mathematical Foundation for Computer Science. Are you talking about the same subject? Acha, discrete computational structures. Wow, nice name. Nice name, sir. See, in GATE, the weightage for discrete mathematics, or this Mathematical Foundation for Computer Science, or whatever discrete computational structure, whatever you're calling it, the weightage would be around 8 marks to 10 marks, my dear friends. 8 marks to 10 marks. The weightage would be around 8 marks to 10 marks. Not just 6, my dear friends. Who said 6? 6, then you should ignore this subject. 8 to 10, sometimes it may go beyond that also. They'll combine these questions with probability. So, most of these synthesis type of questions comes from this, sir. 8 to 10 is minimum. Okay? Yeah, less than or equal to m, na? So, how many functions are there? 4 power 4. This is 4 factorial. So, that would be the answer. That would be the answer. See, discrete mathematics is highest weightage subject, sir. Not less than 8. Minimum 8. Okay? Actually, mathematics and discrete mathematics, generally they are saying total weightage is 13. But it is not 13, sir. It will go beyond that actually. Because mathematics, maximum 4 marks you will get it. Engineering mathematics. Remaining 9 marks though, from discrete mathematics, definitely it should come. But because of its, relation with other subjects, you can expect more marks from this. Yes. Number of 1-1 functions from set A to set B. That's what I said. When both are equal, number of 1-1 functions is equal to n factorial, my dear friends. Yeah, everything. See, group theory, you may expect one question, sir. Generally, it's not regular, but on and off they give you that one question. Graph theory, compulsory, minimum 2 marks, maximum 4, 5, 6 marks also they asked. Graph theory may go beyond 2, minimum 2, 3, 4, 5, all are possible, my dear friends. Minimum is 2. Compulsory 2 marks you will get it from graph theory. If you don't get 2 marks from graph theory, that is not a computer science paper. So number of onto functions, we have this particular formula for onto functions, sir. Okay, this formula is derived using inclusion-exclusion principle. So generally we write it like this: MC0. This minus 1 power I will give you alternatively plus minus signs. M power n minus MC1 m minus 1 whole power n plus MC2 m minus 2 whole power n. Like that you continue, sir. When this fellow becomes 0, you stop it. That is the logic, my dear friends. Graph, that's what I am saying, sir. 2 minimum. Minimum 2 marks, 100%. 3 also we can take it, my dear friends. 3 also can be taken, but okay, I am giving you the worst case scenario. 2 to 5, yeah, 6 marks you can expect from graphs because of its linking with algorithms, data structures, even in theory of computation. Like that, if you consider, the weightage should be more. So composite functions. Okay. Now suppose f is a mapping from A to B. F is a mapping from set A to set B. And G is a mapping from set B to set C. See here, circle notation when you write, the second function you write first, then circle first function. G circle F. This is a mapping, then G circle F is a mapping from A to C, my dear friends. It is a mapping from A to C. And this G circle f of x is defined as G of f of x. So if you want G circle f of x, it is G of fx. That is, x is mapped to fx, and that fx under G is mapped to G of fx, my dear friends. So that is the idea, my dear friends. Ankit Singh, see, previous year questions will guide you to prepare how much. Okay, it's not like sufficient. In GATE, they generally don't, repeat that. They don't repeat, my dear. See, Tushar, whether it is function or relation, they are sets, sir. They are sets. Am I clear? Function a minus b will not be there. Actually, function f1 minus function f2 will be there. Function a minus b, are you talking about function of a minus b? I don't know. It should be proper, sir. Function of a minus b. How can you define function of a minus b, sir? Some set na function of. See, what is actually happening, sir? We can have this a minus b as a set. We can have a minus b as a set. So that you may be mapping to something else. That can be the situation, my dear friends. Okay? You have to see the context. Blindly, we cannot take that, function a minus b. A minus b, you cannot take it as a function, sir. A minus b will be a set. If a and b are sets. You can have function of a minus b. See, my dear friends, sources of practice depends on how you are preparing it. See, are you doing self-preparation? Are you preparing from some coaching? It depends on that. See, if you are preparing from a source or a coaching or from a particular person, even outside also if you are preparing, you should follow his ideology, my dear friends. But generally, if you want to understand just like a layman, you don't want to take any coaching or anything, in that particular case, you have to take the standard books. Okay? See, for discrete mathematics, the standard books are Rosen. Okay? Then there is called Kandel book. Then we have Tremblay and Manohar. Then we have, what do you call that? Ross, what do you call that? Coleman Busby. See, these are different books, my dear friends. Okay? So, you take the books, try practicing solved questions first, then practice as many example or exercise problems as you can. See, generally what people do, they keep this solution manual. Nowadays, in the net situation, we have all these available on the net, my dear friends. The solution manual. They keep the solution manual and they feel that they done it. That is the most useless thing, my dear friend. Don't do like that. Am I clear? You have to solve the problems. Don't keep solution manual. Do at least one problem on your own, that is great. So without solving, you keep 1,000 problems solved. What is the use of it? Okay? Yeah. See, composition need not be commutative. First thing is composition of two functions. composition of two functions need not be commutative, because G circle f of x need not be equal to f circle g of x, my dear friends. See, sometimes even if G circle f is defined, f circle g need not be defined only. So even if it is defined, they need not be equal, my dear friends. But the composition is associated. Composition is associated. Am I clear? Associative property is satisfied, but not commutative property, my dear friends. See, in group theory, this is a very famous question, my dear friends. That is set of all functions under composition. What happens? Closure property satisfied, associative satisfied, identity function will be there, identity is satisfied, inverse function is there. If it is, bijective functions are there, no, inverse is possible. Commutativity will not be there, so it becomes only group. It cannot become abelian group. So that type of questions are useful, okay? Because of that, we learn these properties, my dear friends. And interesting thing, suppose you are having a function from A to B, function from B to C. F is A to B, G is from B to C. Suppose F is 1, 1, G is 1, 1, then G circle F is also 1, 1. If F is onto, G is onto, G circle F is onto. See, ISRO also same story, sir. See, when you prepare for GATE, mostly the syllabus for whatever examination is there, that will be done, sir. Only thing is, there may be some topics like, discrete mathematics and algorithms, they may be concentrating more logical topics, they'll ask you more, my dear friends, in depth. That you just need to go through the previous year question, then you can understand. That's it. Am I clear? So, combining these two, if F and G both are 1, 1 and onto, then G circle F will be 1, 1 and onto, my dear friends. But the reverse is not true. See, if you see this, I'll give you one example. Now, if you observe, this is F and this is G. Now, directly I consider that, sorry, where is it gone? Okay. So, directly I consider G circle F, sir. G circle F, okay, I don't have space, I'll write it here. G circle F, I write it here. It is from A to C, sir. It is from A to C. So, G circle F is A and C. So, F is mapping from 1 to A, 2 mapped to Q, Q mapped to B, so 2 mapped to B. If you see G circle F, it is both 1, 1 and onto. G circle F is both 1, 1 and onto, but if you see F is 1, 1, but not onto. F is not onto. And if you observe, G, it is onto, but not 1, 1. So the converse need not be true, my dear friends. See, BYQs, I already told you about that. BYQs will give you the idea what topic to prepare and where we need to concentrate more, because from somewhere you will be getting questions very regularly. See, for example, if you observe logic and graph theory, questions are asked more. So these topics can never be missed. Group theory, they are asking a very basic questions which are relational or result based questions. So minimum at least you try to know the results. That is at least what results I discuss. If you know it, it would be generally sufficient. Rest of the thing is depending on examination, my dear friends. Like that. So if G circle F is 1, 1 and onto, we can't say F is 1, 1 and onto, G is F 1, 1 and onto. But what is interesting is, if G circle F is 1, 1, G may not be 1, 1, definitely F will be 1, 1. If G circle F is onto, F may not be onto, but G will be definitely onto. So the partial converse result is true. That is very important, my dear friend, for GATE point of view. And that is the result. If G circle F is 1, 1, F must be 1, 1. Don't know about G. If G circle F is onto, G must be onto, but F need not be onto, my dear friends. And combiningly, if G circle F is 1, 1 and onto, F is 1, 1 and G is onto, the others we cannot see. This is very important question or important result, my dear friends. See, if F is a mapping from A to B and IA is a mapping from A to A. Oh, sorry, let me clear this because I need to write this. Then what happens? F circle IA, that is first you have to use, see F is a mapping from A to B, no? You cannot have B to A, no? So you can have IA which is mapping from A to A and F here. Then we can have F circle IA will be equal to F, my dear friends. F circle IA. For example, it is 1, 2, it is AB. And F is a mapping to, say this one, whatever it is, 1, 2, like this. Then this is, 1, 1 function. A is mapped to 1, B is mapped to 1. And you see what is happened, sir. Again, this F circle IA is mapping same as, it is mapping from A to B. 1 is mapped to 1. Am I clear? I'm sorry, here we should call it as AB only, no? Here we should call it as AB only. AB only we should call it. A is mapped to 1, B is mapped to 2 only. So exactly same thing will be happening, sir. It is working as identity function. But what I want you to understand is where it should be operated. IA should be operated on right here, whereas if it is IB, it should be operated on left. IA should be operated on right. Right in the sense, IA should be first in the circle operation. And IB should be second in the circle operation. Then what happens? You are going to get identity function. But if F is a mapping from A to A, in that case, no problem. Whether you do F circle IA or I circle FA, it does not matter, my dear friends. Same is the case for inverse. This is also very interesting. If F is a mapping from A to B and F inverse is a mapping from B to A, if you do F inverse circle F, F inverse circle F, that is F inverse circle F means first is F, next is F inverse. It is from A to B, it is from B to A. F inverse circle F will be mapping from A to A. That is, you are going to get IA. But instead, if you take F inverse first, that is B to A first, then F next, that is A to B. In this particular case, what happens, sir? This is called F circle F inverse. What is it? F circle F inverse. It is an identity function from B to B, my dear friends. Am I clear? It is from B to B. That is the case. But if F is a mapping from A to A, whether you write F inverse circle F or F circle F inverse, they will be one and the same, my dear friends. They will be one and the same. And this is very important result. There was a gate question of worth 2 marks based on this result. Generally, when you see F circle F of X is equal to X, what people see, people simply feel that F is identity. It's not necessary that F is identity, sir. Even if F is F inverse, what happens? Element is mapped to itself. It becomes identity, my dear friends. So, when F circle F of X is equal to X means F can be identity or F can be equal to F inverse. F can be equal to F inverse. So, this is a very interesting result, sir. There was a gate question based on this. So, now we move on to relations on A topic, sir. We move on to relations on A topic. Reflexive. See, a relation from set A to A is called relation on A. We have different types of relations which need to be discussed. Reflexive relation means for all A belonging to A should be related to A, then we call the relation as reflexive. And irreflexive means for all A belonging to A should not be related to A, then we call it as irreflexive relation. Symmetric means if A related to B, then B should be related to A. That is symmetric relation. Asymmetric means if A related to B, then B should not be related to A, my dear friends. जाना है क्या? अभी नहीं बताऊंगा password. Antisymmetric, if A related to B and B related to A, then A must be equal to B, my dear friends. A must be equal to B. Am I clear? That is antisymmetric relation. Transitive means if A related to B and B related to A, then A should be related to C. So these are the 6 important definitions one should know, my dear friends. And out of these, if a relation is reflexive, symmetric and transitive, it becomes equivalence relation. If it is reflexive, antisymmetric and transitive, it becomes partially ordering relation, my dear friends. Now, this is wonderful result, my dear friends. Please note this. If you know that a relation is reflexive, its inverse is also reflexive. If it is irreflexive, inverse is also irreflexive. Symmetric, inverse is also same. Asymmetric, inverse is also same. Antisymmetric, inverse is also same. Transitive, inverse is also same. Same is the case if R1 and R2 are reflexive, their intersection is same. If they are irreflexive, their intersection is also irreflexive. If they are symmetric, their intersection is also symmetric. Asymmetric intersection is also asymmetric. Antisymmetric intersection is also antisymmetric. Transitive intersection is also transitive, my dear friends. Union of reflexive relations is reflexive. Union of irreflexive is irreflexive. Union of symmetric relation is symmetric. But these are the three failure cases. Please remember, my dear friends. Right? Hope you understand. Now these are the cases which we need to understand as need not be. Need not be. So union of two antisymmetric need not be antisymmetric. Union of two transitive need not be transitive. Union of two asymmetric need not be asymmetric. You just need to remember this entire table, sir. And in the table only 3 cross marks. If you remember, you know 18 results. So I given 18 results at a time, my dear friends. Am I clear? I given 18 results at a time. Now look here, sir. Suppose A is a set having n elements. A cross A contain how many elements, my dear friends? A cross A contains how many elements? See, we all know it. A cross A contains n square elements. See, these are the n square elements. Suppose 1, 2 and so on, n square. Number of relations are there. What do you mean by relations from set A to A, sir? It is a subset of A cross A. See, if you want to form a subset, for each element there are 2 choices. It may be present or it may be absent. Present or absent. Present or absent. Present or absent. Present or absent. 2, 2, 2, 2. How many times, sir? N square times. So what is the answer, my dear friends? 2 power n square is the required answer. 2 power n square is the required answer, my dear friends. And using the similar procedure, I am revealing the biggest secret of the day, the most important result of the day, and password also. Here only I am revealing the password. Gate 323. What is it? Gate 323. That is the password up to relations. That is the password up to relations. For graph theory, second part will be there. That will be done later. At the end, graph theory ka bhi password milega. So up to relations, this password, sir. Gate 323. Okay? Gate 323. That is the password. Password for your, okay, the formula series or formula PDF up to relations. So counting relations, if A is containing n elements, type and count. Number of relations is 2 power n square. Number of reflexive relations is 2 power n into n minus 1. Number of irreflexive also exactly same, that is 2 power n into n minus 1. Number of symmetric relations will be, actually this would be 2 power n into n plus 1 by 2, or you can remember like this, 2 power n into 2 power n into n minus 1 by 2, or 2 power nc2 also people remember. 2 power nc2 also. This is how people remember, my dear friends. Number of asymmetric relations will be 3 power n into n minus 1 by 2 or 3 power nc2 also you can remember. Then number of antisymmetric relations would be 2 power n into 3 power nc2, my dear friends. 3 power nc2, my dear friends. And reflexive and symmetric relations. Number of reflexive as well as symmetric. Actually, symmetric is 2 power n into 2 power nc2, my dear friends. When it is reflexive and symmetric, this 2 power n becomes, because reflexive pairs must be present, so only 2 power nc2 will be the answer. That is 2 power n into n minus 1 by 2. The most important results, my dear friends. On this, they can ask you direct gate questions. For example, they can give you A is equal to 5 and they can ask you any of these questions. They can ask you probability questions also based on this. A relation is selected on a set containing 5 elements. What is the probability that it is a symmetric relation? That also can be asked. So this is one of the important powerful rules, okay, table, my dear friends. Now suppose R is a relation on a set A, then you generally call it as, R is actually reflexive closure, sir. Reflexive closure. What is reflexive closure? Smallest reflexive relation containing R. Smallest reflexive relation containing R. Is the idea clear? And what is this reflexive closure? How to get it, sir? Simply R union delta. Delta means reflexive. That is one equal to relation. Delta means equal to relation. Delta is equal to relation. Am I clear? Now, suppose if R is reflexive, the reflexive closure will be same as R, my dear friends. Warshalls is very important, and the time complexity of Warshall is also very important, sir. Floyd-Warshall algorithm and Warshall algorithm, the idea would be same. There we find all-pairs shortest path algorithm, whereas Warshall algorithm gives all-pairs path algorithm. That is the difference between them. Now, RS is symmetric closure. What is it? Symmetric closure. Symmetric closure. Smallest symmetric relation containing R. And how to find symmetric closure, sir? Just do R union R inverse, sir. You are going to get symmetric closure, my dear friends. And R is symmetric if and only if R is equal to its symmetric closure. And then comes transitive closure, my dear friends. Transitive closure, either it is denoted by R plus if the set is finite, or infinity if the set is infinity, sir. It is transitive closure. See, transitive closure also you can find it by regular method, my dear friend, but this takes long time. That's why you use Warshall algorithm, my dear friends. Am I clear? R is transitive if and only if the transitive closure is equal to R, my dear friend. Then R is transitive. So generally to check whether R is transitive or not, it takes actually long time, my dear friends. It's very difficult one. So what people do is they find the transitive closure. If the transitive closure is same as the relation, then R is transitive, my dear friends. And how to find transitive closure, sir? You have to take R union with R square. R square means what, sir? RR. R cube means R square R. R power n is R power n minus 1 R. So doing that and taking union of all those fellows will give you transitive closure. But by this method, if you do it, 2-3 days it will take. So that's why what we do, we use Warshall algorithm, my dear friends. That's why we do Warshall algorithm. Of course, I am not discussing Warshall algorithm here. There is a procedure. Because anyhow, I am not discussing algorithms here. In discrete mathematics, generally I don't discuss, only procedure I discuss. But in algorithms, Floyd-Warshall algorithm, together with that, I discuss Warshall algorithm. Am I clear? Now, a relation, कौन सा टेबल से सॉल्व कर सकते हैं? कौन सा टेबल? That is what? That matrix method, you can do it. See, adjacency matrix के बिना भी कर सकते हैं, diagraph से भी कर सकते हैं. You can use diagraph, my dear friends. Diagraph method is much easier. Because adjacency matrix, suppose if it is having 4 vertices, it's fine. If you are having 5 vertices, you have to take 5 by 5 matrix. If you are having 6 vertices, you have to take 6 by 6 matrix. So instead of using adjacency matrix, diagraph method is much better for Warshall algorithm. Am I clear? Diagraph method is better, my dear friends. Nishu, diagraph method is better than the adjacency matrix. A relation which is reflexive, antisymmetric and transitive is what is called as partially ordering relation. And a set together with a partially ordering relation is what is known as partially ordered set. P-O set, poset. And the most important posets are set of integers with less than or equal to, set of positive integers with division, and power set with subset are the most popular posets, my dear friends. And remember, whenever a relation is a partially ordering relation, its inverse is also partially ordering relation. Because you know, if a relation is reflexive, its inverse is reflexive, relation is antisymmetric, inverse is antisymmetric, relation is transitive, its inverse is also transitive. Therefore, whenever relation is partially ordering relation, the inverse also partially ordering relation. So whenever P with a relation is poset, P with its inverse is also a poset, and these fellows are called duals, my dear friends. They are called what? Duals of each other. And the most important duals these are. So set of integers with less than or equal to is a poset. Set of integer with greater than or equal to is a poset. Any subset of set of integers with less than or equal to is a poset, and same with greater than or equal to is a poset. Any set of positive integers with division is a poset. Set of positive integers with multiple of relation is a poset. Any subset of set of positive integers with respect to division is a poset. Same set with multiple of relation is also a poset. And power set with subset is a poset. Same power set with superset is also a poset. And set of positive divisors of n with division is a poset. Same set of positive divisors of n with multiple of relation is also a poset, my dear friends. And a poset in which every pair of elements comparable is what is known as two-set, totally ordered set or linearly ordered set or a chain. So what happens? In a chain, what happens? Every pair of elements are comparable. Suppose if I give 1, 2, 3, 4 with respect to less than or equal to, every pair of elements are comparable. So you can write them one after the other. It becomes two-set. But with respect to division, can you arrange them like this? It is not possible. Why? Because there is no total order. We have only partial order here. So for representing partial order relations or a set with containing only partial order, we use Hashi diagram, my dear friends. And for Hashi diagram, we need to know two important things. One is called associated relationship and covering relationship. Okay? And suppose P be a poset and every element in P denoted by a small vertex like this. And suppose B is covering A, the circle of B will be above circle of A and A joins B with a single straight line. And suppose A is having associated relation. Associated relation means nothing, sir. A related to B but not equal to B, and B does not cover A. That means, see, covering means between those two there is no other element. If there are no other elements between, does not cover means there may be many elements. So you can reach B by series of vertices. So series of edges you may reach A to B, my dear friends. That is the idea. So that is how Hashi diagram is constructed. So this is actually procedure, but we generally use shortcut procedure. But here I cannot teach you the shortcut, my dear friends. So you need to attend one of my classes to understand the shortcut for finding or drawing Hashi diagram, my dear friends. See, for Hashi diagram when you draw, there are two elements which are special elements. One pair is called minimal maximal elements. See, minimal elements means, what do you mean by minimal, my dear friends? There is no one above, no one below it, that is minimal. Maximal means there is no one above it. Okay? So generally, the elements which do not have horns, are maximal. The elements which do not have, tail are the minimal elements. They should not have, see, if this is there, there should not be any edge going above that. So such element becomes maximal. There should not be any edge going below that. Then it is minimal element, my dear friends. And in general, the maximal and minimal, if exist, they need not be unique, my dear friends. See, here you see this. If you see this A, B, C, D, E, here A, B are minimal, D, E are maximal. There can be many maximal, many minimal, my dear friends. And finite poset, if it is there, definitely maximal and minimal exist. But infinite poset, for example, infinite poset means set of integers with respect to less than or equal to. This is a poset, my dear friends. And here there is no maximal, no minimal, my dear friends. So infinite posets need not have maximal and minimal elements, but finite posets 100% will have maximal and minimal elements. See, greatest elements are little intelligent. What they say, everyone is related to me. Everyone is related to me, then it is greatest. Least means this fellow is related to everyone. Okay? So we generally denote greatest by 1, that notation, and least by 0, my dear friends. And if at all greatest and least exist, they must be same. Only one greatest and one least, my dear friends. And see, as I told you, maximal can be many, minimals can be many. But if maximal is only 1, that is greatest. If minimal is only 1, that is least, my dear friends. And next comes upper bound and lower bound. Then we also introduce greatest lower bound and least upper bound, my dear friends. And we use this notation for greatest lower bound of two elements. We denote it by A and B, and we also read it as A meet B. And this is called least upper bound. We denote it by A or B, or we also read it as A join B, my dear friends. Yes, correct, Tushar, very good. Now for standard relations, we can find GLB and LUB, sir. Suppose if the relation is less than or equal to, for two elements, if you want to find GLB, it is simply minimum of the two elements. Minimum of AB will be the GLB, maximum of the two elements will be the LUB, my dear friends. Suppose if the relation is division relation, the GLB will be equal to GCD or HCF, whatever you call it. GCD of the two numbers will be their greatest lower bound, and LCM will be their least upper bound, my dear friends. Suppose if the relation is subset relation, the GLB will be simply intersection of the two elements or the two sets, and LUB will be union of the two sets, my dear friends. Am I clear? There is one very important property, my dear friends, called consistency property. So to check whether the given poset is lattice or not, this is the most powerful result. The most powerful result. What it says is, if two elements are related, okay, anyhow I am writing it. If two elements are related, definitely LUB guaranteed, GLB guaranteed, my dear friends. And what is a lattice, my dear friends? A poset is a lattice if every pair of elements, for every pair of elements, LUB, GLB exist, then it is a lattice. A poset becomes lattice when it becomes lattice, sir. For every pair of elements, you can find LUB and GLB, then it becomes lattice, my dear friends. And to find LUB, GLB for two elements, if they are related, 100% LUB, GLB exist. And in chain means what, sir? Every pair of elements are comparable. Means every pair of elements are related. Comparable means in some order they are related. So obviously this fellow becomes lattice, my dear friends. So a chain is 100% lattice because of this consistency property only. You don't have to verify anything. Directly consistency property can give you that result. Now, once you know it is a lattice, 100% guaranteed are the four properties. In a lattice, idempotent property is satisfied. In a lattice, commutative property is satisfied. In a lattice, associative property is satisfied. And in a lattice, absorption property is also satisfied. So by default, in a lattice, these four properties are 100% satisfied, my dear friends. By default, these four properties are 100% satisfied. But distributive properties need not be satisfied in a lattice. But distributive inequalities are 100% satisfied, sir. These are called distributive inequalities. So in a lattice, this was a gate question long back, sir. In a lattice, distributive inequalities are 100% satisfied. But there are some lattice in which distributive properties are satisfied. In a lattice in which distributive properties hold good are called distributive lattices. And the famous example for distributive lattice is power set with subset relation. This is a famous example for a distributive lattice. In this lattice, 100% distributive properties hold good. And the bad fellows, in which distributive properties does not hold good, only distributive properties hold good, are two famous fellows. One is called diamond lattice and the other one is called pentagon lattice. Whatever, I think it's wrong. Let me draw properly. See, these are the bad fellows which are not distributive. Famous non-distributive lattices are these. These are famous non-distributive lattices. Famous non-distributive lattices. Am I clear? Like that. Now comes bounded lattice. See, in a lattice, if greatest and least element exist, that is called bounded lattice. But finite lattice, 100% greatest and least will exist, my dear friends. So there is no need of worrying about that, my dear friends. Okay, and infinite lattices, and the famous example for infinite lattice which is not bounded is again your set of integers with less than or equal to. It is infinite lattice which is not bounded, my dear friends, which is not bounded. And set of integers with less than or equal to is the example I already written. Now, you know, complement of its element means what, sir? The complement of the element A is such that A or B is greatest element and A and same B is 0, then B becomes complement of A. B becomes complement of A. And if A is complement of B, B becomes complement of A and vice versa, sir. And for greatest element, least is the complement, and for the least, greatest is the complement, my dear friends. Now, if it is a chain, with 3 or more elements, complement does not exist. Chain only with 2 elements complement exists. If it is having 3 elements, no complements, my dear friends. It is not complemented lattice. See, complemented lattice means what, sir? Every element should have a complement, that is complemented lattice. Every element should have a complement, that is complemented lattice, my dear friends. And in a distributive lattice, see, generally, even if complement exists for a single element, there may be multiple complements, sir. This is a very popular example, sir. See, if this element is A, B is a complement for this, C is also a complement for this. Okay, suppose if you have this particular, whenever you see this example, you can easily say this. Okay. A, B, C, D, E, F, G. So for A, the elements in the other lines like E, D, G, F becomes complements. So for one element there can be multiple complements, sir. But if it is a distributive lattice, for one element only one complement will be there. See, it may not guarantee complements, but complements if exist must be unique. That is what it says. Now set of all, and the important thing which we need to know is bounded. This is the definition for Boolean algebra, sir. Bounded distributive and complemented lattice is Boolean algebra. Bounded, distributed and complemented lattice is Boolean algebra, my dear friends. Bounded, distributed and complemented lattice is Boolean algebra. And the famous example for Boolean algebra is, suppose Dn with division is there, no? If n is product of distinct primes. For example, you see D30. 30 is what? 2 into 3 into 5. If it is product of distinct prime factors, then Dn with division becomes Boolean algebra, my dear friends. Dn with division, that is D30 with division, is Boolean algebra. And this is the condition, my dear friends. It should be product of distinct prime factors. It is product of distinct prime factors, my dear friends. Now, equivalence relation means a relation which is reflexive, symmetric and transitive is called equivalence relation, my dear friends. A relation which is reflexive, symmetric and transitive is called equivalence relation. And whenever R is an equivalence relation, you can find equivalence class of an element. Equivalence class of element is set of elements which are related to that element. The elements which are related to A is called equivalence class of A. And remember that every element belongs to its equivalence class, and if B is in equivalence class of A will be in equivalence class of B. Okay, and two equivalence classes will be either completely same or completely different. Now the important formula is, if A is containing n elements, then number of equivalence classes or equivalence relations on A will be same as number of partitions of A, and that is equal to Bell number, my dear friends. And this is the famous formula for Bell number, my dear friends. See, for example, it is how it is written. Let me tell you. If it is Bn, my dear friends, so what actually happens here? Okay, we are going to start with n minus 1 C0, B0, n minus 1 C1, B1, plus and so on, n minus 1 C, n minus 1, B, n minus 1. So this is how we can get the value for Bn, my dear friends, and it is one of the important formulae, my dear friends. Suppose if A contains n elements, A cross A contains n square elements, then number of elements in smallest equivalence relation on A will be n, because the smallest equivalence relation on A is delta relation, and number of elements in largest equivalence relation is n square, because largest equivalence relation is A cross A, my dear friends. And this we already seen, my dear friends. This we already seen. These are ticks, these are ticks, these are ticks, but only transitive union need not be transitive. Similarly, inverse of a equivalence relation is equivalence relation, intersection of equivalence relation is equivalence relation, but union of equivalence relation need not be equivalence relation, my dear friends. Yeah. Of course, congruence modulo is an important equivalence relation, sir, and congruence modulo equivalence relation divides the set of integers into m equivalence classes. and the equivalence classes are given here. Okay, all of you able to follow? Is the idea clear? All of you able to follow, sir? We completed relations. So far, any doubts? So far, any doubts? So now let us start with the algebraic structures, that is groups. So suppose there is a non-empty set S and there is a binary operation star is there. Okay. So when you call that particular binary operation is closed on S, or S is closed with respect to star relation, sir, if you do operation between two elements, the resultant must belong to the same set. Then you call it as closed under that particular relation. What do you mean by associative? Whether you do A star, B star, C, yeah, A star, B star, C, the answer is same. What do you mean by identity, my dear friends? E is an identity. If A star E, yeah, E star A, you should get back A, then you call it as E is an identity, or we say that identity exists in the set with respect to the relation. And what do you mean by inverse, my dear friends? What do you mean by inverse, my dear friends? B is called inverse. If A star B, yeah, B star A should give you identity back. And what do you mean by commutative, my dear friend? A star B is equal to B star A, then you call it as commutative relation, my dear friends. Now, suppose we have a non-empty set and a star relation, only closure property satisfied, then you call it as algebraic structure. I think it is going in a reverse direction, sorry. Algebraic structure means only closure property satisfied. Semi-group means closure plus associative properties must be satisfied. Am I clear? Monoid means closure, associative, identity must be satisfied. And group means closure, associativity, existence of identity and existence of inverse are satisfied. Then you call it as group. And a group in which commutative property satisfied is what is called as commutative group, ya to abelian group, my dear friends. Of course, here this entire story is all about verification of these properties, finding identity, finding inverse. Nothing more than that, my dear friends. But the properties we should make note of it. So most of the people are having trouble. So what I am doing is I am giving complete list of the results which we should know. I am giving complete list of results at least we should know. Okay. See, this group theory is one semester course for some people, my dear friends. Generally, even in our regular course, maximum 2-3 hours, we complete group theory. Am I clear? So we should understand how to do it as a topic. Okay. Otherwise, if you overdo it, what happens? You will get only sleep, not marks. Please be careful. Now, in a group, identity is only one. Only one identity will be there. For an element, only one inverse will be there. And inverse of whole inverse, that is A inverse whole inverse will be A. And AB whole inverse is reverse order. B inverse into A inverse. And identity, suppose E is an identity, inverse of identity is itself. Inverse of identity is itself. And suppose if group is having even number of elements, other than identity, you can find at least one element whose inverse is itself. That is, we can find an element which is self-inverse, my dear friends, other than identity, if it is having even number of elements. Then a finite group of order less than 6 is always abelian. Suppose he gives order of group is, which of the following is always abelian? So he'll ask you like this. He'll ask you the question like this. Which of the following is always abelian? Which of the following group is always abelian? Okay, first one, a group with order equal to 4. B, a group with order is equal to 5. A group with order 6. A group with order 8. Which of them is always abelian, my dear friend? This type of question can be asked. Here it is a multiple choice or multiple select question. Is it a multiple choice or multiple select question, sir? See, these two are compulsory abelian, these two are not. Am I clear? Like that. And every group of prime order. Suppose if the order is prime, 100% abelian, sir. Suppose if I given 7, even though it is more than 6, because it is prime order, it is also abelian, my dear friends. Hi, sir. Jagan Mohan. Hi. Welcome, sir. Now, these are the important groups, my dear friend. The set of non-negative integers from 0 to m-1 with addition modulo m is an abelian group, and set of positive integers less than or equal to p-1 when p is prime number is an abelian group, my dear friends. And you know, if you know a group, the subgroup can be identified just with this property, because a subset which itself is a group is called subgroup. But if you want to prove that a subset is subgroup, you have to verify all the properties: closure, associative, existence of identity, and existence of inverse. But without doing all that, just by doing this property, we can verify that it is an abelian group, my dear friends. It is an abelian group, my dear friends. Am I clear? So that is what, sir, A star B inverse belongs to H for all A, B belong to H. If you do it, then it becomes a subgroup, my dear friends. But if it is a finite group, you don't even have to do this much work. If it is a finite group, what we just need to do, sir, A star B belongs to H. If you do it, it's enough. That is a wonderful property, my dear friends. Now, this is the most powerful result. And what is this result says, sir? Lagrange's theorem. H is subgroup of G, then order of H divides order of G. See, my dear friends, H is subgroup of G, then order of H divides order of G. See, my dear friends, if the condition is in P, that is called sufficient condition. If the condition is in Q, that is called necessary condition. This is a necessary condition but not sufficient, my dear friends. This is a necessary condition but not sufficient condition. And subgroup of abelian group is 100% abelian, sir. If H and K are subgroups, their intersection is subgroup, but their union need not be a subgroup. But if one is contained in other, like H is subset of K or K is subset of H, then H union K also will be subgroup. Now this is called order of an element, sir. Order of an element M is equal to, you say that A is of order M if you can find a positive integer, smallest positive integer M, such that A power M is equal to E. That is, A operated with itself M times, you should get identity. If that M is the smallest positive integer doing that stuff, then we can call it as order of an element, my dear friends. And a group in which order of element is equal to order of group is what is called as generator of the group, sir. Such an element is called generator, and a group having generator is called cyclic group. A group having at least one generator is called cyclic group. Is called cyclic group, my dear friends. It is called cyclic group. Now, if it is prime order, 100% it is cyclic, sir. You don't have to verify, whether generators exist or not. 100% it will be cyclic. That is, there will be a generator. Suppose if I give order of group is 11, is it cyclic or not? Is it cyclic or not? Without verification, directly you can say, yes, Babu, it is cyclic. Go to home. You can say that. And every subgroup of cyclic group is cyclic. Every subgroup of cyclic group is cyclic, my dear friends. And every cyclic group is an abelian group, but not conversely. Okay? So, cyclic group, if it is an abelian group. But every abelian need not be cyclic, my dear friend. That you need to remember. Now, this Euler's 5 function which we discussed under set theory, that can be used here, sir, to find number of generators. Suppose it is a cyclic group, okay, of order n, and he asks how many generators are there. You can simply use this phi n, Euler 5 function, to find that value, my dear friends. And of course, if you know order of element, you also know order of A power K, my dear friends. So this is about groups. And the last topic is graphs. Are you ready for graphs? Quickly, let us review the properties of graphs, my dear friends. Are you ready for graphs? So for graphs, what is a graph? My dear friends, a graph is an ordered pair of two sets, V and E, where V is called vertex set and E is called edge set. Because it is an ordered pair without vertex set, there is no edge set. If each edge is identified with unordered pair of vertices, then you call it as undirected graph. And each edge is identified with an ordered pair of vertices, then you call it as directed graph or simply digraph, my dear friends. Digraph, my dear friends. Now in a graph there can be self loop, there can be parallel edges. Suppose if you are having a graph in which there are no parallel edges, no self loop, such a graph is called simple graph. If in the graph parallel edges are allowed but self loops are not allowed, then you call it as multi-graph. And a graph in which parallel edges allowed and self loops allowed is called a general graph ya to pseudo graph, my dear friends. The first theorem of graph theory says is, in any undirected graph, the number of, that is the sum of degrees of all vertices, degree means number of edges incident on a vertex, the sum of degrees of all vertices is equal to twice the number of edges. And the most important result, my dear friends. Okay. Now, second thing is, in any graph, the number of odd degree vertices will be always even. Now, look at this graph, sir. I am just drawing a big graph. Here, let us see the degrees. The degree is 3 here, degree 2 here, degree 3 here, degree 2 here, degree 2 here. So if you add the degrees, 2 plus 2 plus 3 plus 3 plus 2. So what is the sum, my dear friend? 6 plus 6, 12. And here how many edges are there? How many edges are there? Sum of degrees will be, sum of degrees of vertices will be twice the number of edges. That will be satisfied. And you can see number of odd degree vertices 2. See, always number of odd degree vertices will be even. That is, it can be 2, it can be 4, it can be 6, it can be 8, even number. It can be 0 also. Number of odd degree vertices can never be odd, my dear friends. And this is the most beautiful relation, my dear friend, and the most powerful, important relation. This is the most important relation, my dear friends. Okay? And what it says? The minimum degree less than or equal to twice the number of edges by V minus is less than or equal to capital delta. See, generally in problems what happens is, they will be giving, like, he may give number of edges is equal to 13 and minimum degree is 3. Then what is the maximum number of vertices? You simply do 2E by delta with less than or equal to. That is V less than or equal to 2 into 13 by 3. The floor of that will give you the answer. So this type of problems are very, very famous and very, very important, and it is the most powerful result, my dear friends. Hope you understand. Right. Now in any simple graph, there are at least 2 vertices with same degree. At least 2 vertices will have same degree, my dear friends, and degree of a vertex in a simple graph will vary from small 0 to n minus 1 maximum. And this is called Havel-Hakimi theorem, sir. See, Havel-Hakimi theorem says what, sir? Is degree sequence is graphic, means with the degree sequence you can construct a simple graph if and only if the sequence obtained by deleting the highest degree and subtracting one from the remaining one, still it is also graphic, then the original degree sequence is graphic. This is one of the important result, my dear friend, for solving problems. They give you a degree sequence and we need to verify whether it is graphic or not. Now, in a simple graph, maximum degree will be n minus 1 and maximum number of edges would be n into n minus 1 by 2, that is NC2, my dear friends. Now, if it is a bipartite graph, the maximum number of edges will be n square by 4. This was a gate question, sir. If it is having 6 vertices, and it's a bipartite graph, maximum number of edges would be 6 square by 4, my dear friend. That is 36 by 4, that is 9. And if it is a bipartite graph, in bipartite graph, every cycle is an even cycle. Every cycle must be even cycle. This is a wonderful result to verify whether the graph is bipartite or not. Suppose if I give you a graph like this, you can immediately say whether it is bipartite or not. Because here there is an odd cycle, it is not bipartite. It is not bipartite. Okay, so these are some regular graphs, my dear friends. Am I clear? Suppose you are having a graph, Nn is 0 regular graph and Cn is 2 regular graph. Only W3 is a regular, sir. It is 3 regular, but Wn for n greater than 3 is not a regular graph. Complete graph is n minus 1 regular graph. Regular graph is what, sir? A regular graph is a graph in which degree of every vertex is same. If degree of every vertex is k, we call it as k regular graph. And suppose you are having a k regular graph, you know how many edges it will contain? Nk by 2. The number of edges in a k regular graph would be Nk by 2. Because sum of degrees of vertices will be equal to twice the number of edges, no? Because every degree is k, how many times? V times. So, kv is equal to 2e. So, number of vertices would be equal to what, sir? Oh, sorry, number of edges we want, na? He is calling number of vertices as n, no? So, let us use that. Kn is equal to 2e. So, e is equal to kn by 2, my dear friend, or nk by 2. So, that is it. So, the famous graphs and the story table. Null graph will have n vertices, 0 degrees, and degree of each vertex is 0. And cycle graph is having n vertices, n edges, and degree of every vertex is 2. Wheel graph will have, see, wheel graph, the Wn denotes the cycle number of vertices, sir. Wheel graph will have one extra vertex, n plus 1, and number of edges will be 2n, because n in the cycle and n edges connected to the hub. Okay, and again the degree of hub will be n, and degree of non-hubs will be 3, my dear friends. Complete graph, n vertices, n minus 1 is the degree of each vertex, and n into n minus 1 by 2 is number of edges, my dear friends. And Qn, n cube, will have 2 power n vertices, n into 2 power n minus 1 edges, and degree of each vertex is n, my dear friends. And complete bipartite graph, we have m plus n vertices and m into n edges. So here k, m, and no, the vertices of this will have degree n, the vertices of this part will have degree m. And number of simple graphs on n labeled is important, sir. Without labels we cannot find it. So number of simple graphs on n labeled vertices will be 2 power n into n minus 1 by 2, my dear friends. Okay. See, these are some important formulae, my dear friends. See, the remaining formulas, similarly you have to formulate like this. I am stopping this part here. See, this graph theory, the PDF will not be shared now. It will be shared leisurely. The remaining parts PDF will be shared, my dear friends. Okay. So, thank you for attending this session. Please like this session. So, depending on your interest, we can come up with the complete discussion on, because graph theory, the results are few, but the properties are more like, you know, graph coloring properties, standard graphs colors, and other things are very, very important. So, sometime we'll try to discuss that, my dear friends. Okay. So, we try to discuss most of the important properties from discrete mathematics, and on 26th, I'll be coming up with properties on algorithms, my dear friends. That's all for today. Thank you.